Hello, welcome to the presentation with a buzzword in the title. My name is Kamil Szymański. I'm a tech lead at Pragmatic Coders. And today I'd like to discuss what kind of problems reactive streams implementations are trying to solve and how they are trying to solve them. We will be focusing mostly on three main areas of solution space, which is concurrency control, resources utilization, and backpressure. And since this is going to be a live coding session, let me get rid of the slides. All the examples that I will have today will be on a Spring stack, backed by the project Reactor, which is a reactive streams implementation. But this doesn't matter that much because the things that we'll cover today will be pretty universal, common for the reactive streams implementations. So if you favor, for example, Akka or RxJava, you should be able to get as much out of this presentation as you would if you prefer Project Reactor. And before we dive into the reactive world, we'll start with something completely non-reactive, so that we all start from the same page and also so that we have something to compare to. And this will also require you to use your imagination a bit, because what you can see here is a plain old boring MVC style web application that listens for GET requests on one endpoint. And within this endpoint, we have a sleep and return something. I want you to treat this sleep and return 42 as some kind of a blocking operation, like treat it as a database call, calling a downstream service via HTTP, reading data from a file, like any kind of blocking operation. What's important here is that for the sake of the example, it always takes 1 second. So there's no caching, the operating system is not helping us, none of such stories. Just 1 second lasting I/O operation. And having said that, I will have a couple of questions to you regarding this implementation. Like, first of all, what will be the latency of such service? Like this one specific endpoint. 1 second. More than 1 second. Yeah, 1 second is blocking operation. Okay. We also need to like parse the request, the response, but it should be more or less 1 second. We haven't run the service, so let's start it. But for the first request, it will be a bit more than 1 second because we need to bootstrap a couple of things. But the second and all the consecutive ones, requests will be a bit faster. So as you can see, the first one takes way more than 1 second. The following ones are a bit faster. And within this session, we will do a couple of semi-benchmarks. Those won't be proper benchmarks. We won't warm the JVM, we won't warm the application. So I would like you to focus not on the exact numbers that we will get here, but more on the rough values that those results oscillate around. So treat this 1 second, 33 milliseconds, just like 1 second, just for the sake of example. And knowing that we have the latency of 1 second, I would like to ask you how many TPSs, transactions per second, can we get if we hit the service with 5 users at the same time? Any numbers? So I would say 5 would be the answer that I would go for, but because we are proper software engineers, we measure, we do not guess. So let me run Siege. Siege is, in a nutshell, HTTP benchmarking tool. We'll run it in a benchmark mode with 5 concurrent users. Each of them will do 5 repetitions of the whole flow so that we get a bit more trustworthy results. And let's hit it. We can see that it returns HTTP 200s. The response times are around 1 second. And we reach, where's the pointer? And we reach the theoretical maximum of 5 TPSs. 5 concurrent users, 5 transactions per second, because we have 1 second latency. So the follow-up question would be, what result would we expect if we raise the number of concurrent users to 16? How many TPSs? Yeah, I would say that it should be 16, but looking at response times, we won't achieve this result. And clearly, we have some kind of a bottleneck here, because we were able to only reach to... do you see everything? Okay, because on the screen I have it a little bit cropped. We were able to only achieve half of it, and we have some kind of a bottleneck here. You mentioned some kind of a configuration thing. Can you say what would the configuration? Yeah, exactly. Because we are operating here on the MVC style web application, so under the hood we are having the servlet thread per request model. And I've done something nasty for asking such a question to you. I've just set the limit to the worker threads on Tomcat. So we have only 8 of them. Hence, we were able to only achieve 8 TPSs. If we get rid of this limit, we should be able to get more, close to 16. So let's just try it. And looking at response times, we should get close to 16 TPSs. However, we have this limit for some reason. So is there any way to achieve more than 8 TPSs, keeping the limit of 8 worker threads? The only way that I'm aware of to make it happen is to move the blocking operation to some other thread. So let's try to do that. We will utilize the servlet's specification feature, which is asynchronous request processing. But we won't code that to the plain servlets. We will use the Spring abstractions. So instead of string, we'll return a callable of string. And under the hood, Spring will just make a asynchronous processing of this request. So so we have the limit of 8 worker threads, and if we rerun the benchmark, I hope that we will get past the 8 TPSs. And looking at response times, it's looking good. And yeah, we are able to get way past that, reaching out, if we warm up the application, the JVM, to 16 TPSs. However, there is one important piece of the puzzle missing here, because we are executing this blocking operation on some other thread, but we are not controlling those threads. We don't know what is the thread pool that handles those blocking operations, how many those threads we will have. And in the production-grade implementation, we should control that. And obviously, this is possible to achieve. However, this is not that readable as it was. We need to sprinkle our implementation with lots of technical details. Like, we can say that we want to limit the thread pool to 20 threads, but to make it happen, we have to use, for example, deferred result set how it should behave if the operation is successful. If it fails, we, of course, need to somehow execute it asynchronously. Like, the ratio of signal to noise is pretty bad. I wouldn't like to have it in my production systems. I wouldn't like to support it, because what we have here is how we want to achieve things, but the meaning of it, of what we are trying to achieve, is somehow lost in all of those technical details. So let's try to make it a bit better. I will copy this code. I'm copying it only because we will be using the web flags, which is a Spring-provided HTTP reactive component. And let's play a bit with this example. Because we are going reactive, we will use some reactive components here. Instead of callable, we'll return a mono. Mono is a reactive producer that is capable of producing up to one value. So it can produce one value or 0 values. And let's implement that. Let's run it. And because it's reactive, it should be blazingly fast. So anyone would say that we will be able to get past 16 TPSs for 16 users? Okay, no hands. So either you don't want to put your hand up or you know that this won't happen. Because 16 is a theoretical maximum. Sorry, not this service, the new one. But if we run it, seeing the response times like that, we can see that we won't reach even half of it. And I haven't done anything as nasty as previously to set any kind of limit, but the limit is here. The limit is related to the way that we are no longer running on the thread per request model. We are able to achieve only 4 TPSs. And this is because we are running on Netty. And Netty is a blazingly fast networking framework. But because it doesn't run on the thread per request model, instead it uses event loops under the hood. We need to utilize properly those event loops. The 4 TPSs results that we achieved here is related to the number of cores that we are having here. And if you are using event loops, it doesn't make sense to have more event loops that we have cores, because we want to fully utilize them. If we have more event loops than cores, then we run into issues with context switches, so we are losing the performance benefits of this approach. And the result is so bad because we have done something really, really stupid here. We blocked the event loop threads. So again, what we need to do here is to move this blocking operation to some other thread. And this is where the real difference is. Because in order to do that, we can say on which thread, or rather on which scheduler, which you can treat as a thread pool, we should run those operations. So we'll use the subscribe on operator, and we'll use a scheduler. Most of the reactive implementations come with some predefined schedulers, like Elastic here is a scheduler that will create as many threads as we will ask for, and it will also cache them for some time. Immediate means that the same thread that we run it. There's parallel, which means no more threads than we have CPU. Of course, single, which is obvious. We can create a scheduler from executor service. For the presentation sake, we'll use the Elastic scheduler. For production, don't use it because it's unbounded. And let's rerun it, and let's rerun our benchmark as well. So right now, I hope that we won't achieve only 4 TPSs, but we'll get close to 16. And looking at the response times, we are going in the right direction. So we are really close to 16 TPSs because we haven't warmed the application, the JVM. And we have full control over the thread pool, over the scheduler that will execute those operations. And if you compare it to what we had to do previously with all those different result sets, completable futures, this is rather a no-brainer which implementation to go for. But the pros of reactive implementations doesn't end here, because reactive implementation focus a lot on fully utilizing the resources that we have. And to demonstrate that, I will move to another example that I have. Let me run it. This time we are not returning a mono. Instead, we are returning a flux, which is a reactive producer that is capable of producing any number of values. So it can be 0, 1, 3, 3,000, 3 millions, an unbounded stream of values. And here we're simulating generating documents. So each second we are emitting a zero-based integer. We take first 9 of those integers. We make them one indexed, and we map them to documents. And here I would also like you to let your imagination play a bit with this example. I want you to imagine that those documents are really, really huge PDF files, like let's say 1 gigabyte. So we have 9 1 gigabyte documents. Before we discuss what problems are here, let's just submit a request to this implementation. So we're submitting a request, and something doesn't work. It doesn't. Okay. And it does. After like a long pause, we have some kind of a JSON array. Let me maybe time it and pretty print it. As you remember, we have 9 documents. So let's see what's happening here. We wait. And after 9 seconds, we get an array of documents, like each with a number and 1 gigabyte payload. Like this is 1 gigabyte for the sake of example. And if we take a look at the implementation and the request that we made, there are a couple of problems there. First of all, in order to start processing even the first document, we need to wait for the server to send to us all of the documents. So although the server would be able to push to us a generated document after 1 second, we need to wait 9 seconds because this is the time it takes it to generate all of the documents. Moreover, if they are 1 gigabyte large each, we need at least 9 gigabytes of heap just for the sake of serializing it into JSON for keeping the payload. 9 gigabytes is a lot, especially in the era of cloud microservices. And like if we didn't have 9 documents here, but 29, this would mean 29 gigabytes of heap required. If you had 3 concurrent users, again, we need more heap. So the probability of out-of-memory error here is pretty high. And it doesn't end here, because even if we have a server that is capable of fitting all of it into memory, there is still an issue on the client side. Because if the client is not prepared to handle such a big payload, he will inevitably fall into out-of-memory error as well. So we need to do something here. And I would like you to think about how we can improve that for a second. Any ideas? I would try to, for example, serialize it a bit differently. But I'm not meaning to replace Jackson or JSON with reactive JSON or reactive JSON. Those libraries doesn't exist, and I don't see a need for them, because we can do it on our own. Here is a bit of magic of Spring. So I will first change this implementation, then I will show you how it works, and then I will dive what's happening under the hood. So bear with me for a second. We will change a media type here. We will rerun the application. And let's check how handling the request looks like right now. So again, curl. And now instead of returning to the client the whole array of all the documents, each second we are sending just a single document to the client. So after the first second, we are able to send the first document to the client. After 2 seconds, the second document. After 3 seconds, the third, and so on and so forth. So the time to processing first document is just the time to generate one document, not all of them. And also, on the server side, we don't need to fit all the payload at the same time. So instead of having a need of 9 gigabytes of heap, we just need 1 gigabyte of heap to handle the single document. I will dive in a second to the client part, but how it works under the hood. This is part of the contract of Spring Framework, but it works like that. If we get a request, the connection, HTTP connection is opened, and then we are emitting events, emitting documents. So after 1 second, a document is emitted. We serialize this document, this single one document. We flash the response buffer, so bytes start flowing to the client, but we don't close the connection. And it works for each document like that. So another document is emitted, it gets serialized, the response buffer is flashed, we keep the connection open. After those 9 documents are generated, Flags will emit the completion signal. It will emit the signal that says, I'm done. I won't emit any new documents. And if we get this completion signal, if all of the documents are serialized, if all bytes are delivered to the client, then we are able to close the connection. So it's not a magical solution. Frankly speaking, I've been using something like that in the early 2000s or 2011. I guess it was called then Comment by You. There were a lot of hacks. It didn't work flawlessly, but the idea is not new. And frankly speaking, in all of those reactive implementations, most, if not all of the ideas are old ideas from the 80s, 90s. The APIs, the ease of use, the safety of using that is something that makes a difference. And also it makes it feasible to provide such high-level contracts as we can see, for example, here with a Spring that whenever it sees that we want to produce something with a media type of application stream plus JSON, it will actually make a stream out of it, and it will serialize it one object after the other. And we have the issue of time to first document and the memory issue of the server side solved, but there's still a client-side issue. And if this issue is solved, depends on how fast the client is related to the producer. So if the client is as fast or faster than the server, the issue is not existent. If it's slower, then we might get into out-of-memory errors as well. However, there's backpressure on the TCP level. I will dive in a second into backpressure, which is another buzzword that you most probably heard of if you heard anything about reactive. But TCP level backpressure, it's not the application level backpressure. So I won't be able to demonstrate it here, but it doesn't give us ways to control that. And frankly speaking, on HTTP level protocol, especially HTTP 1.1, there is just a recursive response protocol. There's no communication in the meantime. It's just request, response, nothing in the middle. So in order to demonstrate backpressure, I will move to another example. This time, this will be a standalone application. First, let me just run the application to show you what it looks like. What we are doing here, we're querying the document repository. This app. This repository holds 9 documents, and the repository itself returns flags, which is a reactive producer that is capable of supporting backpressure. And then for each of the emitted events, each of the emitted documents, we start processing, we log it on our warn level, then we sleep for 1 second and log that we're done on the info level. The sworn and info is important here. It's just there to let the IDE color it so that we know how it's working. And diving into backpressure, if you heard something about the backpressure, it's mostly described as a backpressure is a way for a customer to tell to the producer that he's too fast and he needs to slow down. And this is a huge simplification. I will make another simplification, but not so huge. So backpressure is a way to dealing with with how fast or how frequently the producer is generating events, and telling him to slow down is just one of the strategies. There's a bit more strategies like that. We can, for example, buffer. We can drop all the events that we are unable to keep with. We can keep only the latest ones so that we don't fill all the memory. We can error out and so on and so forth. But hearing that, you most probably seen that there's at least 2 actors there. There is a client or the consumer, and there is a producer. And between them, we have some kind of protocol. And in a second, we will dive into this protocol. However, before we do so, there is one important thing here. Let me try to do something that we've already seen. So we'll subscribe on the unbounded number of threads, and let's rerun it. So if we have 9 documents, we might expect that all of those documents are processed at the same time. However, this doesn't happen. All of those documents are processed on the single thread, because by default, such kind of a subscription is single-threaded. So it will be processed on the single thread sequentially. And having said that, let me move this part of the implementation into a class. I have prepared it before the presentation, so let's just run it to see if it works, and let's dive into the implementation. The implementation is a bit more complex that it should be, because in a second I would like to play a bit with threads as well. But before we do that, let's see what we can do in such an implementation. So we have a couple of extension points. One of it is hook on next, which basically allows us to react on any event being published. There's hook on completion, which means that all the events were produced. Hooking on errors, on canceling the subscription, and also hooking on the subscription creation point. Because whenever we subscribe to something, a producer creates a subscription for the consumer that requested for that. And let's see how the subscription hook looks like by default. By default, it requests a really large number of events. Actually, it doesn't do so, because long max value is not a huge value. It's a special value. It's a so-called unbounded request, which basically means, hey, producer, give me everything that you are aware of, everything that you will publish. So knowing that, let's try to play a bit with this implementation. So instead of making an unbounded request, let's just request one event. And if we request for this single event, a single event will be emitted, and that would be it. Like if we ask for two documents will be emitted, and that will be it. It doesn't look spectacular, so let's try to do something more here. Whenever we process a document, we'll request for another document. And here, where we subscribe, an event is emitted, and once we process it, another one is emitted, and once this one is processed, another one is emitted, or rather we request for emitting another one. And this is basically how the protocol looks like under the hood, but let's try to play a bit with it. So let's try to process events in 2-element batches. So we'll request for 2 events to be emitted once an event is processed, and hence the mono here, so that we can hack a bit around this design decision for sequential processing, or rather single-threaded subscription. And if we do so, we won't move in 2-element batches, because first we request for 1 document on subscription, and then once it's processed, we ask for 2 documents. So we start processing 2 documents, and after 2 documents are processed, we ask for 2 documents for each processed one. So 2, 4, 8, and the powers of 2. So this is not the way to do 2-element batching. So let's try if we can do 2-element batching. And I have the implementation prepared here. A batch subscriber. Let's run it. It should work. And it does. And this subscriber is a bit more complicated. What it does, it asks for 2 documents on the subscription, and then it checks after processing each document if he processed all of the documents within a batch, and if it's so, he asks for 2 more documents. And we do so using lower level concurrency primitives like atomic integer. And in terms of reactive implementation, we wanted to escape for such a low-level Java util concurrent stuff, because it gets tricky. And whenever we dive into implementation like that, a light bulb should lighten in our head that we're doing something probably improperly, because we shouldn't escape to such low-level primitives. And actually, we're doing so. So I highly encourage you to try things like that, but only for the learning purposes. On production, never do such things without a reason, and probably most of the times the reason will be not valid, because most of the reactive implementations come with a bunch of operators that are already doing stuff that we want to achieve. So in order to process 2-element batches, we can, for example, use the buffer operator. And here we will get events that contain 2 documents. So you can see that each emitted event contains 2 documents to be processed. Of course, this impacts the logic of subscription handling, or rather each event handling. So if we are not okay with that, there's also operators that allow us to do so. We'll just parallelize it over 2 threads, or up to 2 threads. So whenever we dive into using low-level concurrency primitives, we should dive into the API and check whether we are doing that, whether we really need to do that, because more clever guys most probably have done it for us. Actually, at least more clever than me. And knowing how Backpressure protocol looks like and how the clients can play with it, we have only part of the story here, because there is still a producer. And what does it mean for a producer to support Backpressure? Let's check. And for that, I have a simple test. It involves debugging, but it's not that complicated as it seems. This will be a simple debugging session to check whether the producer supports Backpressure. We need to see what's on the heap, how it's producing events and what he's keeping on the heap. And the requirements for that would be that if we are processing those events in a single thread, then it doesn't make sense to fit all the documents on a heap at the same time. We would like to have just a single document on a heap to be processed. So let's check whether it is supported by producer, by JPA producer. Let's run the test first, and then we will check how the implementation looks like. So running the debugger, I have placed two breakpoints here. One is on querying the repository, and the second one is where we have the event processing logic. The first breakpoint is here only to catch the snapshot of the heap. In my IDE, I just open the memory view tab, and if I resume processing, I'm processing the first document that was emitted. So let's check how many documents we have on the heap. And actually, we have 9 of them. So all of the documents that we have in the repository. So let's check how the implementation of this repository looks like, because we are returning a flag which is capable of supporting Backpressure, but it doesn't mean that it supports Backpressure. And it doesn't, because it's impossible. We're creating a flag, but we're creating it from the structure that is already loaded onto the heap. This get result list creates a list that is already on the heap. And in terms of JPA 2.1, it's not possible using the plain JPA. For the JPA 2.2, there's a stream method that a lot of JPA providers implement that allow us to stream results and create a flag from a stream. So let's try to use it. However, we won't use JPA 2.2. We will just use Hibernate that has it for a long time. Let's rerun our benchmark, and let's see how it's working. So we are catching the snapshot of the heap, and then we are moving to processing the first element. And we have just one element on the heap. If we rerun, move on in our debugging, we're processing the second element. So we have 2 elements on the heap. One was just created on the heap. If we continue, we will have the third element loaded here. I needed to type it here because in the recent IntelliJ releases, it doesn't auto-refresh for some reason. So if you want to try it at home, be aware of that. And you might think that at some point of time, the garbage collector will kick in, and it will garbage collect all of the events that were emitted, those documents that were emitted, besides the one that we are currently processing. However, this isn't the case because those are managed entities, so garbage collector won't be able to collect them. And we will dive into this scenario in a second, but before we do that, let's see how the Hibernate implementation looks like. And it doesn't look any more complex than we had previously. For the sake of familiarity, we're using a deprecated version of that, so just to reuse the entity manager from JPA, we unwrap it, and then we open up a stream from the query that we run. And based on this stream, we are creating a flags. So thanks to that, we are able to load only as many events at the time as we are processing. And for the sake of not leaking resources, not leaking connections, we need to make sure that we are closing this stream. So on each terminating event, which means basically either everything worked flawlessly and the flags emitted everything properly, or there was an error, we do a result stream close. One important thing here is also how many Hibernate queries are we making. So let's run this service, maybe this time without the debugger, and let's check how many queries are we making. And this is a place where we are making this query. So it's select all. And this is the last query that we are making. Under the hood, it all depends on the JPA provider, on the database driver, so it can use a DB cursor under the hood. It all depends on what stack are you on. Because it doesn't come for free, you are sparing the heap, but there will be some networking involved here. And to show that, and to also show how to mitigate this garbage collection issue that we are unable to garbage collect managed entities, we will see how the lower level implementation might look like. This is a JDBC-based implementation, and this isn't a production-ready implementation. This is just for the sake of learning how it could look like. So what we are doing here, we're obtaining a connection for our data source. We're setting auto commit to false, just to be able to, for example, use a DB cursor. Then we are creating a statement and setting a fetch size. If we want to optimize how many network round trips are we making, we can say that instead of making a network call for each single document, we might want to load them in like 4 of them at the same time. Of course, this is just a hint for your DB driver. It might ignore it, and then we're executing a query, and we're getting the result set. And the result set is not like a set that is persisted on the heap. It's just a result set that contains pointers to database results. So at the time, it will just hold a single row from the database. And based on that, we convert this result set into the iterator, and we create a flags out of it. Of course, we need to handle the erroneous situations and reading the whole result set. So in order not to leak resources, we're closing the connection. Mapping to the iterator is rather straightforward. However, getting the documents out of the result set is a bit trickier. Maybe not trickier, but it requires you a lot of knowledge about what your domain object looks like in your Java code and how it looks like in your database. So we need here to go to the lower level primitives like getInt, getString, getBoolean, and so on. And this is part of the reason why we don't have a generic implementation on the JDBC that would allow to do that. And having a proper reactive implementation of talking to relational databases, it's a bit tricky because JDBC is by design a blocking specification. There is a work going on to create a non-blocking asynchronous specification that would be an alternative to JDBC, but this is still for the future. It won't for sure be delivered for the Java 11 or 12. And to conclude what we have talked about today, reactive implementations focus a lot on optimizing the resources that you have at your disposal to best use them to process what you need to process. And thanks to that, we get most of the times for free implementation services that are more resilient or more performant. And because of the readable APIs that are well crafted for it, it makes it way easier and way safer to parallelize our flows, to control threading. And this is one of the reasons why you should take a look at reactive implementations. Of course, as usual in technology, this is not a silver bullet. There are some trade-offs. It doesn't come for free. So because of the ease of controlling the threads, we need to get loose on the ease of debugging, because there's a lot of switching between threads. Debugging gets a bit trickier. Also, if you, for example, rely on thread locals, this is also an issue that you would need to think about it. And even if you don't rely on thread locks, a lot of libraries does. If you're, for example, doing some multi-tenant applications, a lot of tenancy stuff goes into thread locals, transactions, thread locals, security. Usually, it also involves some thread locals. So please beware of that, but try those reactive implementations. Let's see if they solve your issues. If they don't bring new ones, just make a conscious decision whether to use them. I highly encourage you to try them out. And with that, I'd like to open up for the questions, if you have any. Okay, I see none. So I hope that this was understandable and you didn't fall asleep. I thank you for coming here and listening to my talk. I hope you find it useful, and I wish you a great rest of the conference. Thank you.